Yeah, I want to start my presentation by thanking the prize committee for selecting me for this talk and for the organizers for organizing this conference. It's a shame we can't be together in person, but hopefully next year. So what I'm going to be talking about today is some recent and a little bit less recent work of my group using novel time series analysis techniques that involve machine learning in ways other than just trying to estimate the dynamics. So this is work done by the Complex Systems Group at UWA at the University of Western Australia. I'm also employed and have a joint chair with the Australian Government Research Agency, CSIRO, where we are looking at applying these sorts of techniques in applications that relate to mineral resources, to the mineral industry, to finding things underground. And also some of this work that I'll show later on is work that's been done through a training center that I'm part of, where we are looking at applying these techniques for problems in industrial predictive maintenance. And finally, should acknowledge some of this is in collaboration with a private company of mine. So before I begin, let me first briefly acknowledge all of the people that actually did the work that I'm talking about today. I did do some of it myself, but there's a lot of other people behind me who are responsible for the bulk of it. This work started out quite a while ago with the work of Kevin and Alistair, my PhD supervisor and mentor, and has been continuing at UWA with other academics, David, Thomas, and Deborah, as well as multiple postdoctoral researchers, AM, who's now moved on to a different position, as has Thomas, and Shannon, and our PhD students, Eugene and Braden. Some of their work will be featured here. Finally, Melinda deserves an acknowledgement as the token engineer in the group, keeping the mathematics honest to some sort of engineering application. So let me start where we always start, at the beginning. And my first question, really the question is not what is a model, but what is a model for? So obviously, there's a whole bunch of different techniques to do modeling, and I'm not going to bore you with the details of all of them. I just want to give a very high level overview from a dynamical systems perspective of what we're doing when we build a model. So we're building a model to mimic the evolution of the dynamical system. So if we have a set of time series observations, we want to try to predict the next time series observation from the current state. And when we say current state, what we usually mean is we perform some sort of embedding. So we're trying to get a function f that gives me a good approximation to zt from zt minus 1 through to zt minus t. So there's some embedding dimension. There's some dimension of history that we're going to use to predict the future. And of course, this is guaranteed by Tarkin's theorem and all of those wonderful results. Models are usually evaluated so that we minimize root mean square prediction error. That is, the model gets as close as possible to the true next state of the time series. There are some issues with this in that it's not necessarily the best way to capture the long-term dynamics of the system, but it's the most obvious and easiest thing to do. So let me give you an example. This is probably unnecessary for most of this audience, but on the left, there's a two-dimensional dynamical system, xt and yt, so each point representing a state of that system. The subsequent state of that system is plotted as a different point on the graph, and there's no temporal connection between them. Whereas on the right, we're plotting a genuine time series. So we're just measuring x of t over time, and those points are ordered, but they're just the x component of that map. Now, I can build a model, and here I'm building a model using some, so this is not actually using reservoir computing, but using a radial basis function approach that I developed quite some time ago. On the left, you can see the true state in blue, neatly hidden underneath my predictions in red, and the errors of those predictions in green are quite small. So if I show you the blue and the red, I'll say, haha, I've done a good prediction because my predicted values are close to the truth. If I then choose to iterate those predicted values to try to reproduce the attractor of the map, the two-dimensional picture that we started with, the truth is the blue points two-dimensional picture that I get from iterates of the model is the red one. So in fact, although my one-step predictions are small, the dynamics of the model are quite different from the dynamics of the map. I can, of course, do better, and here's a reasonably good model. So here, again, on the left, I'm showing the one-step behavior, and you can see between the first one and the second one, there's very little difference perceptible in the one-step behavior, but obviously the attractor that I get, the reconstructed sequence of points in the model prediction, in this case in the red, is much closer to the geometry that I see in the original data. So this I would say is a good model because it's captured the dynamics as well as the attractor of the original system. Now, there's many different ways we can go about trying to get good models, and going back in time to about 20 odd years, we took the same technique, replaced the radial basis functions with polynomial terms, and we can obtain a polynomial model. The advantage of this is that because the model F is now polynomial terms, it is a polynomial description of the vector field of the original system. Now, in many dynamical systems that we study, the vector field can be described by polynomials. So by a happy coincidence that we're using basis functions that are polynomials and our model itself, the truth, is also polynomials, we can just take this model and read off the coefficients of those polynomial terms. So in this case, the model that I'm fitting was evolution of the Lorentz system. And so you can read off here in this table, we have the coefficients and the various polynomial terms. And so you can read off exactly, almost exactly, the Lorentz equations, right? So x dot is 10y minus x, right? 10y minus 10x. With a couple of small terms, which is because are there because we're integrating with a Adams-Euler integrator, so there's a small error there. Y dot is minus y minus xz plus 28x, just as we expect. Similarly for z for z dot. So getting models that capture the equations of systems and so-called capturing the physics and the equations from model data is not difficult in the situations where we have within our model the correct basis functions or the correct terms to build such a description. I mean, this was done quite a while ago, and techniques now exist, techniques like Cindy and others that people have been developing to do essentially the same type of thing with more sophistication and more computer power. So this is nice because we can produce the equations and say, aha, that's my system. But the question remains as to whether or not the model itself is a good model of the dynamics. So the first thing I want to talk about is, given I've got a model, how might I go about evaluating how good that model is? I already gave some hint when I showed those figures early on. I said, well, this one's good because it captures the attractor. This one's not so good because the attractors look different. But the challenge here is, what do we mean by the attractor looks right? So how do we quantify a good looking attractor? Before we do that, still back in the darkest days of history and 20 odd years ago, we might take a statistical approach. And that is, here I'm again looking at the Lorentz system, and again building a prediction. So the solid lines are my mean value of a bunch of predictions and a confidence interval on those predictions, except it's not estimated as an ensemble. It's estimated using something we call the psi-phi paradigm. So clever pun there on psi and phi. It involves actually two linear operators, which were denoted by psi and phi. And essentially what I'm doing is I'm building a prediction with the asterisks as the small dots, like a few steps at a time, and then interpolating on those to fit the expected mean and distribution, which is what's being predicted there. So my model behavior is being characterized by an envelope of future possible states. That's okay in a statistical sense, and it captures one of the features that we expect for a system like the Lorenz, which is chaotic, of course, where we see over time the predictions growing wider, not all the time, but at certain time intervals growing wider as we have increasing uncertainty in our dynamics. But now, if we want to try to actually capture the shape of the attractor and to measure how good the shape of the attractor is compared to the data, we have to be a bit more sophisticated than this. So the next slide contains a lot of details because I'm trying to cram the entire paper from earlier this year onto one slide. But in a nutshell, we have time series observations. We can take those time series observations and we can embed them a la Tarkin's theorem with time delay, with some embedding dimension and embedding lag. We can get a cloud of points. That cloud of points is a representation of the attractor. So it's got the correct shape of the attractor. This is all data-driven just from our observations of the system. Now we then build a model on that data, on that time series, just as people in machine learning do, just as I demonstrated earlier that we can do with straightforward radial basis functions. Here we're doing it with reservoir computers, which I'll introduce in a moment and for the rest of the talk as well. But the basic idea is simply that I've built a model by minimizing my one-step prediction error. I then iterate that model to get a picture of the attractor from the model. I've got the attractor from the original system because I've got the data. I've got as many attractors as I want from the models because I can just generate as much new trajectories as I want from the models because I've got the models. And what I can then do is look at the shape of this attractor. Look at the shape of this attractor for the original system and the shape of this attractor for the model system. Now, an obvious thing to do might be to take these two sets of points and somehow measure the average distance between them. That turns out to be incredibly complicated and sensitive on particular features of the system that aren't really very useful. So, for example, in the original picture I showed you for the model of the Tinkerbell map, the good model was not in exactly the same position as the data, and that would be measured as a systematic error if I was to do that. However, the shape is exactly the same. Well, I claim is very close to exactly the same. So what I want to do is measure the topological shape of that object and compare the topological shape of that object to the topological shape of the true system. Okay. And so the way in which we do that is using a tool called persistence homology. So what I'm doing essentially is using a computational technique called topological data analysis to quantify the distribution of points in a more nuanced way. So the way that this technique works, in essence, is I have a cloud of points, which I'm depicting up here in these 4 diagrams involving all the balls. So starting on the left, I have a cloud of points. I can put a little ball around each of those points. None of those balls intersect, and so I see them as isolated points. I then increase the size of those balls, moving to the right. As I do that, the balls start to intersect. And what I do then is when I see balls that intersect, I say that the corresponding points are connected. Okay, so these 2 points are connected because their balls are touching. None of the other ones are. I increase the size of the balls further, and I see that there is now many of these points connected. So each of these points is connected to the 2 points either side of it. And indeed, on the top right-hand corner here, we actually have these 2 points. You have the same thing. So these 2 points are connected. These 2 points are connected. Okay, so every point connected to its pair. But here also, this point is now connected to the top. So we actually have 3 points in the top of this picture here, where those 3 are connected in a simplex, right, as a triangle. Increase the size of the balls further, and they all become connected all to each other. So you can imagine, as I'm increasing the size of the balls, I'm getting a network, a graph structure, which is changing over time, becoming more dense as I get more edges. And I can think of that graph structure as a simplicial complex that's changing over time. and I can quantify the features of that simplicial structure in terms of simplices and their boundaries. I can also quantify the existence, emergence, and elimination of holes in those structures. If I think of it as a simplicial complex, I can identify the holes in a simplicial complex directly. And so what we do is, for a large cloud of points, we map out the value of epsilon for when this hole first appears. So this is a hole, it's a gap within the connected structure. It doesn't exist at this smaller value of size of the balls, and it doesn't exist in this larger value. But there's some range of epsilon values for which this hole exists. I quantified that hole's existence in terms of its birth time and death time. That's the radius at which that hole first occurs and the radius at which it disappears. So I'm doing this for the entire cloud of points for my embedded time series. I can plot this as a two-dimensional diagram where on one axis I've got the birth time, the other axis I've got the death time of each and every hole. H0 and H1 correspond to different order holes within the simplicial complex. Essentially then, there's a rather straightforward technique which just rotates this diagram through 45 degrees to get what's called persistent landscapes. Essentially, there's a technical reason for this, but it creates something which is a representation of all those birth and death times, but it starts off at 0, goes up to some sort of peak and comes back down to 0 again. And I get one of these structures, one of these lines is representing the birth and death times of all the holes in my attractor at all scales for one attractor. I can do that for each model that I generate. That gives me the ensemble, the gray lines there. I can get a mean of those, which is my typical behavior, and I can compare that to the original behavior that I got from the data. Okay? So essentially, I'm looking at all of the holes in the data, looking at all of the holes in each of my model realizations and looking at the difference between them. And in the right-hand side of the figure here, the first column is a series of these persistent landscapes for different types of systems. And on the right, I'm extracting from this a single measure, which is the deviation between the models and the original data, normalized with some randomization process for generating a surrogate, which I won't go into, but essentially what this does is give me a score of how similar at different length scales, birth and death time on 2 now, at different scales, how similar the original data whole structure is to the model whole structure. 1 meaning that they're identical and it becomes more different at some scales and then becomes similar again. So if I had a quote unquote good model, then I would expect this to be 1 everywhere. As close to 1 as possible means the model is as good as possible. The further it is from 1 for longer, the worse that model is. Okay. And my measure of goodness or badness of the model is simply how different the appearance, disappearance, and life of holes in that attractor are for the data and for the original model. Okay. So has it got the same topological structure as the original system? Okay, so that was a lot of talking to explain this one slide. And now I'm going to show you some of the results from this and try to argue why this is a better, different, or useful way of measuring the topological structure of an attractor rather than doing the other obvious thing, which is just to measure a dynamical invariant. So here I've got 2 different groups of models. These are models, it doesn't matter what these are models of, it's actually models of the Lorentz system, but essentially I measure how, so each dot on these diagrams is a different model and from a different data set. And I'm measuring how bad those models are, 1 being the best and 0 and down to 0 being the worst. So higher is the model is better according to my new score. And I'm comparing that to how similar on the left, how similar the largest Lyapunov exponent is, and on the right, how similar the correlation dimension is on a log scale for the model and for the truth. Right? So another way of characterizing how well my model captures the dynamics might be to measure the Lyapunov exponent or to measure the correlation integral. Is it the same correlation structure? So if my new measure, this conformance, was doing exactly the same thing as these dynamic invariants like Lyapunov exponent and correlation dimension, then I would expect a straight line, or at least a monotonically or an increasing trend. We don't see that at all. And indeed, so the different color points are just for different size reservoirs. I'm using a reservoir computer here, which I will explain in a moment, but essentially different model structures at this stage. And there's no real pattern. There's instances where the conformance is very good and the dynamic invariants go from being terribly different to terribly similar. And there's instances of the reverse where the dynamic invariants are very good, but the model isn't so good. What we do find, however, is when we investigate this, the models that capture the dynamics are the ones for which conformance and invariance are very similar. Just having one of these two things working well, giving you a good measure of agreement, is not sufficient. This is the same calculation with a different size data set. And indeed, in this shorter data set, we actually almost see a reverse trend where we get models that have very good agreement in correlation dimension or Lyapunov exponent, but very bad conformance. And these are models that generally do not capture the dynamics well, even though just by looking at Lyapunov exponent or correlation dimension, we might say they do. It's easier to see, for example, why correlation dimension might not be an ideal measure in this case, because it's measuring simply the dimension of your system. So we have a way of grading models based on topology. We have a way of measuring the structural complexity of our dynamics in the model and comparing that to the truth. Now I want to move back a bit and think about what the model itself is doing in terms of the dynamics of the system we're looking at. So the model class that I'm looking at here are reservoir computers. And the reason that I've been looking at reservoir computers is mainly because they are simple and they're dynamically attractive in the sense that they encapsulate the basic idea of time delay embedding through their own memory structure within the reservoir itself. So in a very, very high level description, what a reservoir is it's a network of neurons that have got some sort of activation function, and I'm driving that with some input signal, and I have some readout signal from the states of those nodes. In equations, what that means is I've got some drive signal here, which is my U. That's my input to the system. My input is then diffused over the different internal states, the nodes UX. So the XTs are the internal states of the system. And each of those internal state nodes is connected up to other internal states with some network structure. There's WIJ. WIJ is a random structure chosen in a sensible way, where there's a lot of literature to define what we mean by sensible. But essentially, these are the internal states, and then the readout Y, the right-hand side, is some linear combination of the states of the things internal to the network. And where these reservoir computers have their power is that, unlike deep learning, which has a similar sort of structure, we don't bother trying to choose the WIJ or the VIK in any complex nonlinear optimization process, which they're chosen randomly. They're chosen randomly so that the network has good properties and that the dynamics exist in a way in which they have good memory and maximal pattern generation. But other than that, these connections are chosen randomly. The only fitting that is done are the RIs, the output layer, which is usually fitted with some sort of regularization attached to it, something like ridge regression or whatever we prefer. So you have some set of input states, feed into the network. The network is recurrent by virtue of the way the WIJs have been chosen. However, the WIJ states are determined randomly. They're not fitted to the data. And we then read the outputs on the other side, the RIs. And the RIs are where the fitting occurs. Now, this type of structure is really nice for dynamical systems because of the recurrence in the network. We have this natural embedding occurring within the reservoir because the input state, once it's fed into the network, there's delayed copies of it that continue to persist with some attenuation inside the reservoir. And so we have access both to a current state and our previous states when we build our output function. So the reason these go by both the names reservoir computer and echo state network, and I'm not going to dwell too much on the exact difference between the two of those things. Reservoir computers is a broader class and does not necessarily have to be constructed as a set of neurons in the way that's described here. There's examples of reservoirs being constructed from all sorts of different physical and mathematical apparatus, from literally pattern generation in a bucket of water, hence the name reservoir computer, through to one example that my PhD students and I and a couple of postdocs worked on a while ago, where we used a agent-based swarm as a reservoir. So the drive signal in red is driving a swarm of agents who are moving about in response to that drive signal. And we then build a model from the behavior of that swarm to try to predict the future behavior of the drive signal, to build a model of what's going to happen next. Now, the reason that these techniques tend to work quite well is that the reservoir creates a large range of possible patterns. It creates an ensemble of different states that are different representations of interesting and relevant features of the system. So you can imagine, although I don't have a movie here, I only have a still picture, you can imagine as the swarm of agents is moving about, each of them is dancing around in some state, which is a representation of something like the drive that's forcing them to move. Okay. That's simply a picture of probability distribution of the same thing. What's actually done is we're driving the reservoir with something like a Lorenz system, looking at where all the swarm agents are moving. We then, to build the readout in an interesting way, we actually build a radial basis layer on top of it. There's a technicality to that. And that gives us a prediction, which here is the red line of the true dynamics, which is black. So actually, this is a pretty poor prediction. But what is surprising is that it's able to predict anything at all. And what is more surprising is that the readout itself, the functions that we're building here to get the readout layer, turns out to be really necessary. And we're still working on a better choice of building these functions so that we can actually get better fits. But it's kind of a neat idea that just illustrates the range of possible things that we can think about as a reservoir. For the rest of this talk, though, I'm going to mean by reservoir simply a set of neural activations connected on a network. So sigmoidal activation functions on a network. And the key contribution and the last message I want to give you from today is the idea that we might be able to use these sorts of constructions, not just as prediction machines, but as ways of generating useful measures of the dynamics in the same way that things like correlation dimension and Lyapunov exponent are measures of the dynamics. We're going to be trying to measure properties of the dynamics of the system that are represented within the reservoir, but have useful physical interpretation for the system itself. Okay, so the basic idea is that, and the reason people look at reservoir computing is that however it does it, it gives a useful representation of the dynamics, and it's extremely computationally efficient in doing so. It's very easy computationally to build one of these reservoir computers. So one way of thinking about this is that the reservoirs themselves are heuristically building good embeddings of like time delay embeddings of the dynamics of the system from which we can just simply compute linear readouts with regularization that allow us to capture the dynamics. So the time series is going into the reservoir is processing that, creating various possible different time delay embeddings right on top of the usual things, all sorts of different embeddings of that. And then we just take a readout from that, which best fits the future we're trying to predict. All right, so this is the formulation that we had before, an input. The input values here is UKs, which are distributed via the matrix VIK across the different nodes on the reservoir. Each of the nodes on the reservoir, each xj, is wired through an adjacency matrix wij to other nodes in the reservoir, and we have a nonlinear activation function with some bias acting on those nodes to give the time dynamics in the reservoir. Then the way in which we build a predictive model from a reservoir is fitting the output layer, the RIs here, through regularization to make those currents, those states of the individual nodes in the reservoir, the XIs, match my desired output. And the reason it works is because of the tight correlation in the memory that we retain in the reservoir itself, but also because of the dimension of this. So our input may be scalar, there may only be 1K, or it may be multivariate, or may be inputting delay versions already. The reservoir itself has many XIs. There could be hundreds and thousands of nodes in the reservoir, and I'm using a regularization on those hundreds or thousands of nodes to estimate my single scalar output, my YT. So the idea of what I'm calling reservoir time series analysis is to skip the readout step altogether and to just look at the internal states of the nodes and seek to come up with good functions G of those internal states that quantify the dynamics of the system. So you can think about this as something like the sort of effort that people go to with things like recurrence quantification analysis. So a recurrence plot is a picture of the recurrent states in a time series, and then the features that we extract from that recurrence plot, recurrence quantification analysis, are heuristic good measures of the interesting dynamics of the system. Okay, so how do we go about doing all of that? Well, I'm going to start with just a few very simple examples. So each of these, so in teal, I've got 3 measures that I'm computing from the reservoir. Very simply, mean activation, covariance of the activation, or the actual parameters of the readout function that would be fitted if I was to build a dynamical system from this. I've got 3 measures in purple here that are simple linear time series methods, or nonlinear time series methods in the case of RQA. So these are the things that we might already think to do to the time series if we didn't want to look at the reservoir at all. And then I've got the extremely brain dead, straightforward first order linear statistics, mean and variance of the signal. Right, so I'm going to quantify these 8 things to see how well I can use them to predict change in the dynamics of my system. So the setup here is that I'm looking at a time series being generated by a dynamical system. It's going to have some sort of bifurcation parameter, and I'm going to switch that bifurcation parameter. It's going to switch in such a way that it goes from chaos to chaos. So it's a chaos-chaos transition, but it's changing the dynamics in some perhaps subtle way. So think of it, one example here is, well, the very simple example is logistic map at different values of the bifurcation parameter. More complicated examples, a Rossler and Lorenz system going from broadband chaos to multi-band chaos, or different other values of the chaotic dynamics. And the name of the game, what I'm trying to do is to use each of these measures to identify that transition in the time series, in the data directly. Obviously, and I'll get to this at the very end. There's a use for this in things like industrial maintenance, where we're actually interested in machines breaking down, and we want to know when the dynamics changes because the machine's going to break down. Okay, so very simple here. On the left, my signal is just IID noise, and I'm just changing its mean. Can I detect that change in mean? So if I look, the yellow diamonds at the top here, not surprisingly, by looking at the mean of the signal, with 100% accuracy, can detect changes in the mean. Looking at the variance, the circles of the signal, with almost no accuracy whatsoever, I can make some guess as to the change in mean by looking at the variance. On the right, if I change the variance but keep the mean the same, now it's the reverse. Measuring the variance can detect changes in variance. Measuring the mean does not detect changes in variance. That hopefully is not surprising. What is more interesting is the extent to which the other measures, which a priori don't know that we're looking at mean or variance, are able to detect change in mean or variance. Recurrence quantification doesn't detect any change because it's all IID noise. So as far as recurrence quantification is concerned, there is very little detectable change. The reservoir schemes do slightly better. Here we do the same thing for different chaos-chaos bifurcation that will transitions between two different chaotic regimes in the logistic map, the Rossler system, and the Lorenz system. And so on the left, we see everything works for the logistic map, which is something that we learn very early on. We look at time series analysis papers. If it doesn't work for the logistic map, it's not worth publishing it. So your first picture is always one showing how well it works for the logistic map. These ones work quite well. And the Rossler and Lorenz, and again, these are chaos-chaos bifurcations. So we can see in some instances the standard techniques performing well or performing less well, but in most cases, with the exception of the mean of the activations of the reservoir layer down here, the reservoir-based functions perform as well as any other method. They do well at predicting or identifying transitions from short time series. Okay, one final test of the same sort of thing. Here we look at the transition where now the transition is actually generated by a randomization process. So I'm generating different surrogates and looking to see whether or not I can identify that randomization. So surrogates generated by shuffling the data. In the surrogate nomenclature is algorithm 0. Surrogates that are generated by randomizing the phases of the Fourier transform, that preserves the linear statistics. That's the algorithm 1 surrogates. We see that both of them, the mean and the variance of the signal, do a very poor job because those are preserved. So they do no better than, they're not expected to be better than chance. The reservoir techniques do increasingly well. The time series techniques tend to only do well with the randomized signal. They don't do well in the Fourier phase surrogate. So what's that saying is that here I'm detecting a change in these, I'm generating a change in my signal dynamics where the linear dynamics is preserved. So the linear statistics can't detect it. The recurrence quantification does quite well, and all of the reservoir techniques do quite well at detecting that change, especially the readout coefficients from the reservoir itself, because these are all nonlinear measures. They're all feeding off nonlinear representations of the data. There's a third picture on the right here, which is when I generate my random signal by mimicking the local linear dynamics of the system. This was what we called the pseudo-periodic surrogate in a paper that I wrote about 20 odd years ago. But essentially, the transition here is one from a deterministic dynamics on a particular local map structure to a random dynamics on the same local structure. And what we see is all of the techniques doing rather poorly. This is a very tough test. except for the reservoir, the predictive model of the reservoir, which actually manages to pick up the fact that we've moved from deterministic to random. So this is actually one of the more powerful results here, the fact that this is actually able to pick up anything at all. Okay, so the general idea here is that we can use reservoirs as a way of understanding and generating useful features for time series analysis for things like detecting transitions and tipping points. It gives us a new suite of possible techniques with which we can identify these sorts of transitions, and it has power above and beyond the traditional linear and nonlinear techniques, which we're comparing it to in these computations here. I'm going to finish in the last couple of minutes just by giving a quick example of actually applying these sorts of methods to real problems and real data. So the problem here is one of identifying in a reservoir identifying with a reservoir computer when an industrial pump, so a pump on an industrial processing plant, is starting to fail. So these pumps have certain characteristics. One thing that happens when they start to malfunction is they go through this process called cavitation. Essentially, the pump starts to vibrate. The bearings then can deteriorate, and wear is increasing the pump, and we want to detect to what extent that's happening. So essentially, I'm doing the same trick that I just described on the previous few pages. I'm using the reservoir to generate a representation of the dynamics of the pump, the actual industrial pump, from a measured time series of vibration of that pump. And I'm then trying to build a model to predict actual engineering measures of the wear and vibration of that pump. And so this is that comparison here between the truth, the actual measure, and what I'm extracting by using a reservoir or various other techniques. I'll just skip forward to the messiest plot, which shows the true results for the actual experimental data. So here, the thing that I'm trying to predict, I don't really want to go into the industrial maintenance of it, but it's the MPSH margin ratio or cavitation number. So these are two quantities that the engineers are interested in knowing. They can measure them, but to measure them directly is difficult and complicated. So we've done that process and measured them directly for a instrumented experimental pump setup. And we then want to try to infer those measures from the flow data, from the vibration time series, in a way which means that we can circumvent the need to do that direct measurement, because the direct measurement is messy, complicated, and dangerous for the engineers to perform. And what we're seeing here is a transformation of a readout from the reservoir computer compared to the actual values of these vibration numbers for different sets of data. And I would love to see a bunch of crosses lined up along each of those black lines, but I'm incredibly impressed that we've actually got any trend whatsoever. It's a log scale here. The fact that it's going up at some rate here, which seems to match the thing that we're trying to predict, is actually pretty good. The fact that we got any indication at all just by a direct computational measure of this is really quite useful. It gives the engineers something on which to base their maintenance schedule and on which to base their decision on having a closer look at the state of that particular pump. So I'm going to stop there and just move on to very briefly highlight the different manuscripts on papers which I've been leaning on for most of this talk. The code is on GitHub for the description length radial basis modeling that I showed at the start. The various papers in the series of papers in Chaos from 2021-22 detail the precision homology approach to modeling and the reservoir computing, reservoir time series analysis techniques that I've been talking about towards the end of this presentation. My final slide is just a quick advertisement, since I've still got 15 seconds left, to say that I'm looking for a postdoc to come to Western Australia and work on methods like this with the industrial maintenance people. So looking at applying these, what I think are really cool dynamical systems driven modeling techniques to real problems in maintenance engineering. If you're interested, please email me or just search with your favorite search engine for UWA and the position number 509666. Thank you, and I believe I'll be live and online to take questions. Thank you for your attention.